Hey, what's up, guys? So today I want to talk about the quantum algorithm that I previous forget to talk about it. Okay, so there are three quantum algorithms that do not need to use the quantum phase estimation. So previous the simple one is the Dodge-Josa. Okay, I want to spend some time to describe the high level interpretation of it, and second one that I described is previously is Burston Bazarani. Okay, and the third one that I described today will be Simon's. Okay. Okay, so I think the technical way to describe why people believe. Okay, so if one want to prove that quantum computing is better than classical, then one can define so-called bound PQP, which is a problem. Basically, simple to say is that a problem that can be efficiently solved in polynomial time. In poly n, if let's say your input is length n, and in using the quantum computer. Okay, or simply speaking, if you want more complexity, more computer science perspective, that you can define the quantum Turing machine, and if your axis belongs to a language that you output with a probability greater than 2/3, some kind of it, right? But simply, and then another is the class called BBP, which is a standard randomized algorithm. So you can see this is you can view this randomized classical algorithm. Okay, and the more precise definition is that if X belongs to a language, that you want your probability X that the Turing machine accept. Let's say you got Turing machine M accept with probability greater or equal to 2/3. If X do not belong to L, then the probability of M reject less or equal to 1/3. Okay, so this is like a standard definition. So the problem is that what is the results, right? So we need to if one want to prove that the quantum computing is actually better than the classical, then the one would try to prove which the BQP is different from BBP, right? But by that definition, BQP is a larger contains BBP. Okay. The simple reason is that in the classical one, if you get a random bit, then you can use a Hadamard in quantum computing. Okay, so let me just quickly remind this is Hadamard. Okay, you can use the Hadamard matrix, so Hadamard for the spin, right? So that you can get the random bit. Okay, but how to? So this is very difficult, right? This is still the open question that whether BQP is strictly larger than BBP. Okay, and but these three algorithms should get something, should give you something interesting results. Okay, which is called the oracle separation. Okay, so let me just say something. Okay, so previously I think this George thought. Let me just describe this. Okay, so the first interesting result is this Dojo-Josas. So Dojo-Josas, this algorithm is very interesting, right? You just ask a function which is this one. Okay, and you promise that the f is either all or 0 for every x, or half x, so half 0, half, or 1/2. Okay, this is called balance. Okay, then your goal is to decide. So your goal is to decide which one f is. So either constant or balance. Okay, so this is definitely if you use a classical, and you want to deterministic, right? Deterministic, then definitely that you need 2 to the -1 + 1, right? This is the because you get 2 to the n inputs. So if you are very unlucky, then you cannot, right? But in we know that in the quantum, right? If you learn this one, that in the quantum, you can get exactly answer by just only one steps. And then you can use BBP, right? In the classical one, that is very simple, right? You use randomly pick. So you get if you just you randomly pick twice, right? And if you randomly pick, let's say 100 times, let's say I did 100 times, and the function is the probability of this function to be balanced. But I get all 0, right? If a function is balanced, then I go 0. There's a chance that function be balanced if I got all zeros. Is this? Right? Let's say I get 100 consecutive zeros. Okay, so actually those algorithms, although separate this exact classical one, but for BPP it didn't change anything. So this problem, Dojo's still belongs to BPP, obviously. Okay, and did not give you more results. Okay, the second one is the Burstyn-Balzarani. Okay, so Burstyn-Balzarani is that suppose your function is still a Boolean function, and you are promised that the f of x is there is some s, which is x, this s. Okay, and this big sum is basically you sum over a bit. So basically you can simply speaking, or you just view x with s in the Ma2. Okay, or some people like to like more number theory, or you can say that this is inner products in the F2. Okay, so this is inner products in F2 to n. Okay, if you view F2 to n is a vector space over F2. Okay, yeah. So and the problem is to find s. Okay, and this is also if you use a classical one, that obviously that you can prove this, right? Because you need to find s, right? So if you want a classical one, you need n steps. You can just put x to be 1 0 0 0 and 0 0 0 1 0 0 0 0 1 0 0 to get this. Okay, so you're simply speaking your classical one. And this is by information theoretical, you can prove that this is optimal. So you can plug f to be 1 0. Let's say you guess oracle, and the 0 1 0 0 1. Okay, 0 and keep going, right? So you need n steps. Okay, but in the quantum that you only get 1 steps. Okay, because you just put Hadamard or something, so which is really interesting. Okay, so this give you a super polynomial separation. Means that in the classical you need n steps, and then in the quantum that you get 1 steps. And this classical one is even stronger that if you consider BBP, right? If you consider randomized, that you still need to randomly pick up something, which is don't change anything. Okay, so Simon's problem is one interesting discussion that very interesting that you want to find. So let me just describe the final results. So Simon's problem is that the example that you can separate this into the classical. Okay, so basically this is oracle separation in exponential time. Okay, so this is very astonishing that you can find a problem that which in the quantum that you really can do it compared to classical, it has an exponential separation. Okay, so exponential separation is better, is better than this previous Balzarani that you only get the super polynomial separation. Okay, but definitely better than this Deutsch-Jozsa algorithm. Okay. Okay, so let me just describe the detail. And yeah, so the detail is the problem is that you give even Boolean function, and you are tell that there are 2 choices. Okay, so this is okay. Otherwise it's true. Okay, so there are 2 cases. The first case is that f is 1 to 1. Okay, the second case is that there is S non-zero, not a zero vector to n, such that f of x equals to f of y if and only if y equals to x, base sum with s. Okay, so in this case, f is 2 to 1. Okay, so this looks like a black box problem, right? There's another black box problem that somebody gives you f, and you need to make sure that f is 1 to 1 or 2 to 1. Okay. Okay. If you do not have this condition, you only know f is 1 to 1 or f is 2 to 1. This is called a collision problem. And I think in collision problem that you can take n to the 1/3 to get a result, right? Okay. So yeah. Okay. So the problem is that if f is 1 to 1, you need to tell me f. You need to tell me is the first case, or in the second case, you need to find s for me. Okay. So you need to find s for me. Okay, and this is simple. Suppose that I already get f of x equals to fy. Let's say I get 2 x and y such that this is true. Then I by definition then I know this. Okay, so I can find s by direct base sum with x. So I get x base sum y equals to x big sum s big sum x, which is s. Okay, so this is simple that you just need to find a collision, and you get s. So you just need to find a collision. Okay. So what is the complexity if you use classical, or even you use BPP? Then this is the collision problem, right? So you want to find 2 collisions, but this is oracle, so you don't know what is the situation. Okay. So you can use the so-called birthday paradox. Okay, so you know birthday paradox, right? So there are maybe 28 peoples, and there are 365 days. So you can let's say this is n, right? And this is square n. So basically, you only need square root of n randomized pick. Then you will find you will have the higher probability. You will have the constant probability that you find a collision. Okay, so for birthday paradox, you need omega square of 2 to n to find a collision, right? Because your total have 2 to n. So this is the classical one that one can prove this is rigorous. The upper this is the rigorous, the best you can do. Okay, this is the only thing you can do is you randomly pick up then until you find collision, and the constant. In order to achieve the constant probability, you need the order of the square root of 2 to n. This is can be proved by using elementary probability theory. If you haven't proved this, then I will post the link below. You can just go to see my birthday paradox video. There's a proof for this. Okay. Yeah, so let me just talk about a quantum. Okay. So let me just talk about idea. So in a quantum idea, it's very easy, right? So suppose you find that y1 up to y minus 1 belongs to 0, 1 to n, such that y1 inner product with s0, y2 inner product s0, yn minus 1 inner product s0s. Okay. And so suppose someone give you this minus 1 y such that this is true, then obviously that you can find you can solve s. Okay, maybe you need another, but it's you need all order of n equations, right, to solve s. And then this is definitely true, right, due to a linear algebra. If n equations are linear independent, if they are linear independent. Okay, if they are linear independent, right, you get n equations, then you will at most take O(n) squared time to solve the Gaussian elimination. Okay, so the idea is that if somebody tell you that order n or n equations, n y1 up to yn such that this is true, then you can easily solve this. Okay. So here comes the quantum part. So it's very simple that you just take 0 and this is n of n, and you take the Hadamard Hn, and you take the oracle UF, and then the Hadamard. You do this, you take this, and you measure this, and then you measure it. Okay. Yeah, this is a corner circuit. Okay, the idea is that once you do this, then you solve this problem. Okay, so this is the model. I think quantum computing is interesting when you see these type of things, which is really amazing. That what the hell, right? Who come up with this idea? Okay, so UF by definition act on X. You need to define a UF, right? So by my I think UF. Let me just define what the act on. Okay, so UF act on X 0n will define X f of X. Okay, so this is the oracle. Okay. Oh, sorry, I'm stupid. There's no hard mark here. This is a straight line. Okay. Okay, so let's do this. Let's do a very simple calculation. So in before this step, this is just 0 and tensor 0. Okay, and for this step, you get 0 and hard mod n 0 0, right? So this will give you, I think I don't need to explain again. Basically, h tensor n with 0 n will give you all the 2 to the n possible combination. So it's x belongs to 0, 1 to n. X belongs to 0, 1, n. Okay, so you get the 1 over 2 to the n summation x belongs to 0, 1 to the n, tensor 0. Okay. Sorry, this is a vector, so I need to take, I get 2 to the n, right? But this is modulo square, right? So I need to take the square root. Okay, so now let's take the function UF. So after UF, after this step, I get 1 over square root of 2 to the n and the summation x f of x. X belongs to 0, 1, n. Okay. Now what do I do? Okay, so this is bad notation that I should first act h to the n at the first qubit as first n qubit, and I finally measure here. Okay. Okay, so let's do to the final calculation. Okay, so our final state psi will be this. Okay, right, you just do this, and you act on this h n with the first qubit. Sorry, first n qubit, and this is easy to prove, right? This h of n of x that you can try to prove by yourself. I don't need to prove it. Basically, it's become an inner product. This is big sum, so it's ma2 into y. Okay, so some people will say this is a Fourier transform of the f2 based on what you are saying, but it's exactly the same thing. Okay, so now your psi become a 1 over 2 to the n. Okay, so x 0, 1, n, y 0, 1, n, minus x, y tensor f of x. Okay. Okay, so now I can take out y, right? I take out y and everything combined to the f of x. Okay, so let me just write down so I can take this. Because I want to measure the second one. Okay, so let me just take y 0, 1 to the n. Okay. Nice shot. Okay, and at least 1 over 2 to the n can go here. Okay, so now let's consider the measurement. Okay, so there are two cases. Okay, so let's consider the okay, so let's consider the f is 1 to 1. Okay, so if let's say f is 1 to 1. Okay, so f is 1 to 1, right? So that means f of x is all different from this. Okay, so that means I mean, let's say let's for example, if I choose y to be 0, right? You get sum over all f of x. Okay, so it's easy to prove the following is right because this f is 1-to-1. So for every given y, this f of x will be whole numbers, right? So -1 to xy do not make any difference. So if it's 1-to-1 and you measure, then you get a uniform distribution. This is not difficult. You can try to prove it. So basically, the probability that the probability you get the y vector is basically you can check this. X belongs to 0, 1 to the n. X belongs to 0, 1 to the n, and what else is going on? Okay, so minus x, y, and the f of x. Okay, and the f of x will be all 2 to a number, right? So you get the this guy square, and then you get 1 over 2 to the n. 2 to the n is 1 over 2 to 1 over 2 to the n. Okay, so you get uniform distribution. Okay, so if you just keep measuring, you get uniform distribution. Oh, by the way, let me just write down. So this is y, right? I can measure is y. Okay. Actually, if you don't need to measure it. You just need to measure this. You just measure, right? You get y. Okay. Right. Okay. In this case, you get uniform distribution, and let's say f is 2-to-1. Okay, so that means there is this non-zero s such that the x direct bit sum with s equals to y if only if f of x equals f of y. Okay, I think in this case that you can easily find you can easily check this, right? Let's say okay, so your probability of p of y still be 1 to the 2 to the n summation of all of big x 0 1 to n minus xy f of x squared. Okay, so if I measure, let's say, okay, let's do this. Okay, so let's see. That means there's a 2f, right? So 2f will hit. There's x and y will hit this f of x. Do the same thing. Okay, so let's consider as fx1 and fx2. Let's say equals to z. Okay, so this guy can be written as 1 over 2 to the n. Let's say z belongs to a. I will write down definition. So let's say a to be the f. So a will be the, let's say a be the image of 0, 1 to the n. Okay. So a will be the image, right? So every f of x will be in z. So let's say it will be in a, right? So let's say z belongs to a. And I can write it as -1 x1 big sum y plus -2 x2 big sum y, and then with the z. Okay. And I take a modulo square. Okay. So okay, so very simple calculation. Okay, so very simple calculation is you get 2 of these, right? So now okay, so very easy exercise is you can write this guy square into 1 over 2 to n, z belongs to a. I can take out -1 xy, right? I can take out -1 x1 y, and then become 1 plus -1 x2 plus minus x1, right? But it should be x2 minus x1, but in Ma2, I can use this. Z. This guy is what is 1 plus -1 sy. Okay. Z. Okay. -1 x1 y, z belongs to a, 1 over 2 to the n squared. Okay, so now very easy to see. If xy is non-zero, okay, this is in the Ma2, right? So s dot y have only 2 cases, is 1 or 0. Okay, so if s dot y is 1, then you get amplitude 0, right? Because -1 to the this is 1, right? You get 0, and the else you get 1 over 2 to n. Okay. So the proof is done, right? If s dot y is 0, then you get 1 over 2 to the n. If sy is 1, you get 0. Okay, that means what? That means you just keep measure, right? So the idea is that you just keep measuring you just do this experiment, you just do this simple quantum, the previous quantum circuit for all of n times. Okay, all n times. Then you will get the nlinear equation. And they are linear independent with high probabilities. Okay, the reason okay, so the detailed reason is that why they are not linear independent. What was the probability that they are linear independent? Yes, so this is a simple exercise, but I think it's interesting. You can prove this. Okay. Okay, so suppose I choose one equation. So let's consider the probability of let's say I measure n times. Okay, so let's say I measure n times. Okay, so what is the probability that everything is a linear independent? Okay, this is linear independent. What is the probability that this is linear independent? Okay, so let's say I measure twice, right? So I measure twice. If n is 2, then the probability of its linear independent is just 1 minus 2 to n, right? Because I first take out one equation, and as long as the second equation is do not the same as the one equation, the first one equation, that I get one linear independent, right? And you can check that what's if what's n equals 3, right, is 1 this, 1 minus this. Okay, and then you can check that if I measure let's say I measure total n times, or measure this. Okay, and then you can easily prove that this is always as constant, right, as n goes to infinity. This is not difficult to prove. Nice one. I say it's very not. I think it's very trivial to prove that this is non-zero. Okay, so basically, if n is large enough, that just becomes a number that you can try to plug in, and then this is definitely non-zero. Right? They're definitely non-zero. Okay. Is it? Yeah. Okay. I think it's definitely non-zero. How should I prove this? Okay, let me just quickly prove. Okay, so let me just prove this, because I find maybe it's a little bit non-trivial. So if you're guys that okay, so the key our goal is to prove is non-zero, right? It's greater than 0. Okay, for general n, or basically more general, we want to prove that this probability that is greater than 0 as n goes to infinity. Okay, I think the trick is very easy, easy, right? If 1 minus a, so let's say I get two numbers, a, b are less than 1. If 1 minus a, 1 minus b is greater than 1 minus a minus b, right? So this probability is is greater than 1 minus 1 over 2 to n, 1 plus 2 up to n minus 1. Okay, so it's 1 minus 1 2 to n, and n minus 1 divided by 2. Okay, so obvious equation is 0. Because as n goes to infinity, then this guy becomes 0. Okay, right? So now we prove the answer. Trivial. Okay, so that means this Simon's foundation, sorry, not Simon's foundation, Simon's algorithms only takes will have this exponential separations compared to the Burson-Vazirani. So I think this is the greatest, the best achievement before Show's algorithm come up. Okay, so see you guys next videos.